Let's take a look at hypothesis tests for paired data. So paired data at the beginning will look like it's coming from two distinct populations. So it looks like a two sample situation, but there has to be some reason to think, hey, wait a minute, that information, there is something that connects pieces of data, something to pair them. So one example would be like firstborn and secondborn twins. Right, those twins are siblings, and so even though you could look at all the firstborn and all the secondborn as separate populations, right, within each pair, you can say, okay, there's a firstborn over here that is connected to a secondborn over here. So when we do that, we can take two data sets and really turn it into one data set. So it's no longer a two population or two sample situation. So in this particular instance, we're looking at several different sets of twins, and we're looking at the difference in their IQs, their intelligence quotient, which is considered to be a measure, at least to some degree, of your intelligence. So all of these scores listed are the firstborn minus the secondborn. So we had two pieces of data, we subtracted to get this one piece of data. And then we go to the next pair of twins. We have two pieces of data, their IQs, we subtract them, we get this number. But the important thing is every time we do the firstborn is the first number, secondborn is the second number. That'll give us more consistent results. So we get these values, and then we have a researcher believes that the firstborn twin is smarter than the secondborn for some reason. So there's some reason that this researcher believes that this is the case. We're going to test the claim at the 0.05 level. So we've got our alpha of 0.05. Now, we want to run through this. We could run through this by hand, but we're going to show how to do this in our calculator. So for starters, we would want to put all of that information, those different values here, into a list. So we're going to put this into, say, list 1. So you can just do stats, edit, and then put those values in list 1. Okay, once those values are in list 1, we're going to go back to stats. We're going to go to tests. We're going to figure out if we can decide which test is best. So here's what we know. We don't have a two sample situation because we started off, it looked like two samples, but we put them into a single list, right, one sample. And we want to run a hypothesis test, right? We're testing the claim, so we're running a hypothesis test. And really the question is then, do we use a z-test or a t-test since we're talking about means, right? We want to test this on average. So if we do that, it really just comes down to, well, do I know S, the sample standard deviation, or sigma, the population standard deviation? Well, since we have a sample here, we can certainly find the sample standard deviation. So it seems like we're going to use S, meaning this is going to be a t-test. So since we're using a t-test, you have options when you're running this. You can either choose data or stats. So since we have all of our data in a list already, we're going to choose data. So if we go into that, the t-test is going to ask us basically, okay, well, a few things. What is mu0, or the null hypothesis mu? What list do we want to go from? And in this case, we're choosing list 1. If we were able to put this in list 1, if you put it in a different list, just update that here. It'll ask us about the frequency. If there are repeated values, sometimes we use another list to have the different frequencies. For us, we can just say 1. So basically everything in this list is represented just one time. And then it will ask us about the alternative hypothesis, essentially. So it'll say, okay, mu, are we curious about that being something other than mu0 or mu0, something less than mu0 or mu0, something greater than mu0 or mu0? Okay, well, remember that the first part of this, again, is acting like our null hypothesis. The second part of this is acting like our alternative. So the null hypothesis would be that, right, there's no difference. So the firstborn and the secondborn, there's no difference in their average intelligence. So that would be, right, a difference of 0. There's no difference between the two. Right? Another way to think about that is if you wanted to know, and that's how a lot of these paired data situations are considered, is the difference. So you can say, okay, mu, the difference is mu1 minus mu2, right? Firstborn minus secondborn. If there's no difference, that would be 0. So the difference, that's really just what we're calling mu0 here. So the difference is 0. Okay. For the alternative, if there's some reason to think that the firstborn twin is smarter, right? What you're really saying is, hey, I think that mu1 is greater than mu2. All right, well, we got to frame it a little bit differently. So we have to think, all right, I think that mu1 minus mu2, so if we just subtract that over, is greater than 0. So it's greater than what we said up here. So we think that mu for the difference, right? That's kind of what this is here. The mu for the difference is greater than what we said here, greater than 0. Right? We think that mu1 is greater than mu2, or that these difference, first minus second, on average, is greater than 0. So we can select that, and then we say, great, if we just have all of those pieces, we can go calculate. So let's calculate that. We end up with a p-value that's fairly large, actually. So we get a p-value of 0.466. And of course, that decimal keeps going. Now, what does this tell us? Well, that's a very large p-value, meaning our results are not very rare under the assumption of the null hypothesis. So we're going to say, well, this is definitely way larger than our alpha of 0.05. Right, so there is no reason that we have, no reason to believe that the null is incorrect. So we're going to fail to reject the null. Again, we don't embrace the null, we just fail to reject it. So we have not built up enough evidence to support the researcher. Right? So we fail to reject the null. We have no evidence to believe the researcher is correct.